Hello, thank you for joining this Fibre Channel Industry Association webcast. Our topic today is on 128 GFC, a preview of the new fiber channel speed. If you've joined through Bright Talk, of course, the slides for this webcast are available to you at the bottom of your console. There's a link there where you can download those slides. Also, if you have any questions throughout this webcast, please type them into the chat window for questions. Your mics are all muted, so we're going to use this chat feature as our place for answering your questions. And we encourage audience participation, so we're really looking forward to having you guys engage with us on this webcast. Okay, today the speakers are listed here. I'm going to moderate the presentation today. My name is Mark Jones. I work for Broadcom as the director of technical marketing in the Emulex division. I'm also on the board of the FCIA and currently serving as the president. Our main speaker today is Mr. Dean Wallace. He's the VP of engineering at Marvell Technology and has a history with QLogic. But Dean also serves also a vital function in our industry standards groups for the fiber channel technology. Dean is the FCPI physical layer standards ad hoc chair in INCITS, and is also the T11.2 vice chair. So we're very, very happy to have Dean explain to us all the details about 128 GFC. And then also we have Kieran Ranabar. He's a product manager from Cisco in the MDS division, and he's also on the FCI board of directors. And Kieran also participates quite a bit in T11. He's involved heavily with the standards community, and his contributions are welcome. Kieran's going to help us today by answering a lot of questions, so he's standing by in case you type in questions. He'll be ready to put up some answers and bring them to our attention. Just a little bit about the Fiber Channel Industry Association. The FCIA is a mutual benefit, nonprofit, international organization of manufacturers, system integrators, developers, vendors, and industry professionals and end users. So we're very happy to be here. And there's a long history with the FCIA. We've been around for over 25 years. We celebrated our 25th anniversary a few years ago. The industry is made up of industry leading companies. So there are companies from just about all areas that involve fiber channel, from component suppliers to storage vendors to server vendors to cables, optics, as well as test equipment. So it's represented by a large group of companies. And then we're very proud of the fact, that fiber channel's done so well over the many years it's been around. We've shipped now well over 160 million ports. So just to go a little deeper, I mean, we do have some very incredible milestones that the fiber channel industry has met at the end of 2022. One of those is that we've surpassed the $50 billion mark in fiber channel revenue. And to think about this, I mean, this goes back to pretty much the beginning of fiber channel over the years, since 1998. We get this data from Quillen Research, who's been tabulating this and has taken over for Del Oro on the counting of fiber channel analyst community stuff. So the $50 billion number is switch ports and HBA ports that are shipped from the equipment manufacturers to either the channel or OEM manufacturers and so forth. So it is a partial count of how strong the industry is. But really, that number is far larger because it's, as it gets sold to end users, there's a lot more cost involved, and that's not including cables and optics and all the ancillary devices and parts that are required to make up an effective SAN. So as I mentioned, there's 160 million ports, and that number is growing at a tremendous rate. Still, you can expect that there's about between 8 and 9 million additional ports added each year. And that is forecasted over the next 5 years to continue that way. And if you think about what's currently in service of that number, if you look at like a 5-year look back, the last 5 years, there's about 35 million ports still active today. So there's a tremendous base of fiber channel being used in the back end of organizations that is doing a critical job of connecting enterprise storage to enterprise applications. So we do a number of things in the organization. One of those is we host Plugfest events, and we have our next Plugfest coming up in the October timeframe. We are gathering interest from companies and those that would like to participate in the Plugfest. So we ask you, if you have any interest, if you're at all involved with fiber channel technology, let's say you're integrating the next version of 64 gig fiber channel or 128 gig fiber channel into your devices, and you want to attend a Plugfest or you have interest, please click on this survey and let us know who you are and what you'd like to see. Okay, our agenda today is, we've already talked about the fiber channel milestones, and we'll go over that in a little bit of a look back. We'll talk about some fiber channel terminology, and then Dean's going to take us deep into 128 GFC and what all went into making up that new standard, both on the physical side and on the framing and signaling side. We'll talk a little bit about optical transceivers and protocol changes required for 128 GFC. And then we'll wrap this up by talking about the future roadmap. Where do we go from here? And the roadmap is very bright. And then, of course, we'll answer your questions at the end. So just looking back, if you've been in the industry, let's say these 25 years or longer with fiber channel, this probably looks familiar to you. But back in 1988 is when work actually started on fiber channel to replace SCSI connectivity. And we've gone from 1 gig to 2 gig, and we picked up fabric services and virtualization and converged networks, all the way to the point where we're at today, where NVMe over fabrics is primarily transported over fiber channel on arrays. And we're in this mode now, we're converting between 32 GFC to 64 GFC. And of course, we're going to talk about 128 today. So it's been a long road. And the way this works, it doesn't come about by accident. The standards are not developed within the FCIA, but in INCITS T11. But at the FCIA and T11 work very closely together. We have a very tight relationship in that the FCIA talks to customers. It helps bring in the needs that customers have and what's required for their fiber channel standards. We bring those into INCITS. INCITS works on that and confers back to us, and we help promote it in the end. So we're, like this webcast today, we're promoting the next version of fiber channel. And so we want to make sure that all that hard work that happens there in the standards group is promoted, and the end user community is well aware that fiber channel is alive, well, it has a very robust future. So just thinking back about all these different speeds of fiber channel, you might wonder, well, if you develop the first speed, 1 gig, and then you develop the next speed, 2 gig, what happens in that transition? So this is a look back at all those different generational changes. And you can see that, once the next speed comes along, that there is a time when the earlier speed, its shipments peak and then start to decline while the next speed takes over. And that gap is about 3 to 5 years. We've had some times where it shrunk down to 3, but generally it kind of ends up at 5, and that's pretty much where we're at now. And you can see in this chart here that we're actually at an interesting point where 64 gig fiber channel is just taken over from 32 as the predominant speed, and 16 gig is starting to really slow down and phase out, just as 64 gig is really starting to take off. So it's an interesting way of looking at the dynamics of the fiber channel industry. Okay, now I'll turn it over to Dean Wallace. Dean's going to dive right into the physical standards for fiber channel. So over to you.
Hey, Mark, thank you. Hi, everybody. It's Dean. I'll walk through some of the rest of these slides now. I thought one of the good places to start would be kind of a quick tour through what I call the acronym soup that's fiber channel standards. Basically, the fiber channel standards that we're going to focus on in this presentation are the physical interface standards, aka they will all be labeled PI, FCPI. And then the other group on the protocol side that works very closely in conjunction with physical interface standards is the framing and signaling group. all the things we need for training and speed negotiation and special requirements that we come up with in the physical interface group, then the framing and signaling team has to figure out how to best incorporate them. And so a number is appended to the acronym, especially for PI, that corresponds to what the upcoming standard would be. So PI 9 is going to be 256 GFC. You can see as you walk through this, PI 8, which is what we're talking about here, is the 128 GFC. There have been some parallel standards in the past, so they are basically 4-lane parallel, and a P is appended on the back of the standard for those to indicate that it's parallel. So the FCPI8 starting requirements, every time, and Mark had alluded to this, every time we start a new standards development, we pretty much get a marketing requirements document. It says, okay, this is what we would like the committee to do, whether they could be speeds, doubling the data rate, or backward compatibility. So for 128 GFC, it had to be backward compatible to 64 and 32. Backward compatibility and plug and play to utilize existing infrastructure with new speeds is always a must-have for FC development. Everybody familiar with FC knows it's really important that we could have a 128 GFC HBA or switch, and you could plug 64 or 32 GFC optics into it, and you can communicate over the existing optical infrastructure. So existing cable assemblies, they must plug into the products. Typically, and you'll see this in a later slide, we've got an LC connector, and fiber channel, unlike some of the other variants, is primarily an SFP form factor. So it's LC connector and an SFP form factor. For 128, the reach goals were 100 meters for the multi-mode short reach optical variant, and that's using OM4, OM5 cable plants. The multi-mode optical variant has been the primary fiber channel variant. OM4 has an optical fiber has a higher optical bandwidth than OM3, so you can get a longer reach on OM4 than you can OM3. And in a later slide, you'll see OM3, I believe, is about 60 meters reach. There's also a 10 kilometer that's a single mode optical variant that uses 1310. And then we also do a clause that is an electrical variant for backplane applications. So, and the goal was 128 GFC doubles the throughput of 64 GFC. And we're always given a corrected bit error rate target. And you'll see later we use FEC and other things to get there. Our target is 1e to the minus 15. But really the goal, as everybody knows, is pretty much to have no errors in operation. That's always kind of the target we have. So milestones. So 2023 INCITS T11, we've completed FCPI 8, which is the 128 GFC single lane spec. It's actually, it's in public review right now at INCITS, and will be a published standard, I think, pretty soon. I'm assuming probably in the August timeframe. Once we get through, we have various stages, but once we go to T11 letter ballot, which is where the framing and signaling standard is now, then at that point, I would say the standard is technically stable. We expect in public review really very few comments, and typically the comments we would get in public review are of the editorial type. We have an internal letter ballot where all the experts in the subject matter try to make sure that they clean up the document kind of in its entirety. So when we go to T11 letter ballot, again, there's not technical comments that would impact the standard. And then in 2023, INCITS T11, they approved the FCPI 9 project, which is a 256 GFC single lane specification. And we have started work in that ad hoc already. In fact, we just recently had a meeting that had 18 presentations. So we're kind of moving along quickly with that. And the framing and signaling group has also has a standard approved called FCFS 7, which will be the framing and signaling that goes along with the 256 GFC single lane. So progress continues to move forward. I think this gives you kind of an overview of the fiber channel variants that we have in FCPI 8 and subclauses in the document that go with them. So we have a long wave version. It's 1310 nanometer. It's basically half a meter to 10 kilometer, and that's in section 5.4. We have an intermediate version that's single mode. That's a 2 kilometer version. We have the multi-mode version of basically OM3 fiber, which is 850 nanometer, and that has a 60 meter reach. And then we have the OM4, OM5 version, which has a 100 meter reach. And then I will point out that these are the optical reaches. The electrical interface to those modules is agnostic to what kind you plug in. So you can plug in a multi-mode module, you can plug in a single mode module, and the electrical interface that goes to the host chip, that is going to be unchanged. So that's a good thing. And then there's also a backplane variant, the EA variant that's in clause 7. That variant basically doesn't specify what the copper media is. Really what it does is specify what the overall loss budget would be and the parameters that would go with that budget in order to be able to close things. I think this gives you kind of a high level signaling rate abbreviations. And if you look at this, I think what you'll see is the acronym, we tend to use 1, 2, 4, 8, 16 GFC. We keep doing that. And then you have the signaling rate in megabaud. And initially, all the way up to 32 GFC, we were NRZ, or some people like to refer to it as PAM2. And then if you look at the documents, the signaling rate or the data rate in the documents in the table, the half duplex rate, it's listed at 800 megabytes per second or 1600 megabytes per second. And you can see a big change, and the industry followed this change. The last 32 GFC, which ran at 2805 megabaud, was NRZ. For 64 GFC, what happened, Fibre Channel and other standards bodies, they made the transition from NRZ to PAM4. So now basically you get 2 bits in one UI. And the trade-off in those kind of things is always deciding, is it harder to resolve in the time window, or is it harder to resolve in the voltage window? And then as you can see moving forward, and one thing I also want to highlight, we did this, but you notice the baud rate actually did go up. And the reason it went up is we needed more coding gain from the RS spec. In 32 GFC, we had a Reed-Solomon 528, 514 FEC, and we could do that because we incorporated a transcoding, also a 256, 257. When we went to 64 GFC, we needed a more powerful FEC, Reed-Solomon 544, 514. And we didn't have a way through coding or transcoding to gain any more of the parity bits we needed. So in order to accompany that, we had to increase the line rate to accommodate the additional parity bits we needed. And then as you go to 128 GFC, which is where we're at now, you didn't get a complete doubling. A doubling would have been 115.6, and we ended up at 112.2. When the team of experts that works in this stuff looked at how we could keep the requirements the FCIA wanted on length and close budgets and still get the error rate that Fibre Channel wants, it was decided, look, we can go to 112.2. 115.6 we thought would be a real stretch. So that's how we ended up at that point there. And one of the other things that didn't come across accidentally either, it was picked so that as you look at backward compatibility, which is really important to Fibre Channel, that you could easily go backward compatible with PLL dividers to the backward rates. And then our goal moving forward for 256 GFC, which is the one we've just started on, right now we're saying, look, our plan is based on the requirements we get to try to do 112.2. And we'll see as time goes on and we get more input, whether there's any issues with that or not. But this kind of gives you a high level when we talk fiber channel and a certain acronyms used, what the signaling rate is, how many lanes it has. In this one, I put all the number of lanes, what the modulation or signaling is, and then the actual data rate in megabytes per second that we run at.
Hey, Dean, just a quick question. Is there any reason why 128 GFC module shortwave doesn't show multimode fiber? Is there any reason for that?
No, 128 GFC will use the multimode fiber. I mean, it will run on OM4 and OM5.
I think it was maybe a typo on the last slide, basically.
Oh, it could be. Let me go back. It could very well be. So, oh yeah, exactly. So you guys, that's an omission on my part, a typo. So these, good catch, somebody. These are 128 GFC multimode variants and the 128 GFC backplane variant. So yeah, good catch. Yes, and these are the 128 GFC reaches. So.
Right. Thanks, Dean.
And we talked about this a little bit already, and I'll just highlight it quick. The modulation refers to the signal levels that are on the wire and the physical interface, whether it's optical or electrical. And the optical and electrical encoding and wire rate are the same. I think one of the things that's really important, and we'll talk about this a little bit later for fiber channel, is what is transmitted on the host electrically. The data rate and the modulation is not changed through the optical module. So it's a complex module now because of the equalization needed, but it doesn't have to do any additional FEC in the optical module, and it doesn't have to do a translation of the speed. So for 128 GFC, the module would get electrically in basically a PAM4 modulated signal at a 112.2, and it will generate on the fiber an optical signal basically that's 112.2 PAM4 also. And 64 GFC basically was exactly the same thing. No conversions within the module at all. What's generated by the host, whether it's HBA ASIC or switch ASIC, is also the same signaling rate and modulation that's used on the optical link. And 32 GFC, that, as stated previously, that was NRZ and PAM2 with a line rate of 28.05. And I think it's important to see the distinction here because 2 levels of backward compatibility is always key. In the standard, the framing and signaling standard, they specify 4 levels of backward data rates of backward compatibility, but with the modules, usually there's the primary rate and 2 rates back. So it is important to understand, if you buy 128 module, you would expect it to be able to speed negotiate to 64 and 32 also.
Hey, Dean, just one more question. Sorry. I think the audience is very well engaged, so that's great. The question is, can you comment on the speed selections here? They're not exactly double, going from 32 to 64 to 128. Is there any particular reason for this, and will that break any backward compatibility or anything like that?
Yeah, good.
And one more follow-up on that is, can you also confirm the exact speeds? Is it 112.2 Gbps for 128 gig?
Yeah, I can. So good question. So 2805, which is the NRZ, that was an exact doubling of the 14.025. And a distinction here, the 16 GFC rate, that had a much simpler FEC. It had a fire code FEC that in a lot of cases wasn't even needed optically. It was used electrically. For 32 GFC, we needed to go to a Reed-Solomon FEC, and what we picked for the coding gain that was needed was a Reed-Solomon 528, 514 FEC. We actually could do that. We have 6466 data that we transcoded to 256, 257. So we actually could get the coding gain of the Reed-Solomon FEC because we did transcoding without having to increase the line rate. So it basically was a doubling. For 64 GFC, we wanted to double the throughput in megabytes per second, but we needed a more powerful Reed-Solomon FEC to be able to close the link budget. So we picked the Reed-Solomon 544, 514 FEC to go with that. That has 160 more bits per FEC code word for the parity. So there was no way for us to go ahead and get that by any kind of transcoding or tricks with the data stream. So we had to increase the actual line rate to basically get the same overall doubling of throughput in megabytes per second, but we needed the additional line rate to compensate for the FEC, for the more complicated FEC to close the budget. And then for 112.2, a doubling for this would have been 115.6, but we felt when we started doing the analysis of where that was, where the technology was, both for SerDes technology and optics technology, the group felt that they couldn't get 115.6. We felt we couldn't close the timing budget, or we would need a much more powerful FEC, which would have consequences too, because obviously then we'd need to run at a higher data rate. So you kind of get yourself in a box, and the team did a really good job of analyzing this. So what kind of the intermediate we came up with was like, okay, we can run at 112.2, and this was picked because the rates make it easily backward compatible to the speeds that are slower speeds without having to do anything odd with fractional dividers or anything like that. So hopefully that kind of answered the question of how we ended up here. And then the target for 256 GFC, which is just starting, would be a doubling of 128 to 224.4 using PAM4. And I think as the committee works and goes on, we'll see if that's actually achievable or not. And I think we talked about this. This just kind of highlights, PAM4. You basically are getting 2 bits per symbol. Kind of like we talked, the trade-off is you can get a little wider UI in the time domain, but you have less in the voltage domain to resolve. And the experts that do this work, there were a lot of trade-offs looking at signal to noise and CDR locking and things like that, how to get what for these particular rates seem to be the best path forward. And I think you would find when you look at other standards, whether it's IEEE, OIF, et cetera, everybody pretty much at whether it's 50 gig or 64 GFC, those kind of speeds made this transition to PAM4 signaling. And then optical transceivers for 128 GFC, fiber channel optical transceivers, are clearly a big part of this and how you interface to them. They're used for both short reach multimode and long reach single mode. They utilize PAM4 signaling on the optical cabling. So the data rate and the signaling is the same electrically into the module, optically out. And I highlighted that in the next bullet. And the optical transceiver has a clock and data recovery circuit in the module on both the transmit and receive path. So the CDR in the optical module does reset the jitter path there. And I think one of the other things that I want to highlight here, and this played a big part in the complexity moving forward, when historically in NRZ signaling, the optical modules, they had equalization in it, but it was a simpler, I would say, analog-based equalizer, and you needed a lot less time and less information going to the host ASIC. When standards moved to 64 GFC, and of course following up to 128, the complexity of the equalization in the module became much more complex. And in many cases now, it's a DSP-based equalization in the module. So then that gave a whole new set of parameters that the teams had to take into account timing wise, because you needed time for that DSP equalizer to adapt to the incoming signal. You had to wait, if you were a host ASIC, till it provided the signal quality electrically you needed to be able to start your adaptation. And you needed to have a level of communication between the two so you knew where you were. So there were a lot of work and a lot of interoperability things that were learned at 64 GFC that I think that the teams that develop these standards have taken into account, and I believe will make things much more seamless as we move forward at 128 GFC. So, and I think, 128 GFC has SR, medium range, long range modules that are optical and electrical. They're in an SFP 112 form factor. There's an SFP 56 form factor that was used for 64 GFC technology. And they're standards based. One of the big things I highlighted in here is, as we go from 64 GFC modules to 128 GFC optical modules, there's work being done. It's called CMIS, and it's a common management interface. And these modules, and that development is being done within the OIF. Historically, standards developments for the modules like 8472 have been done in the SFF group. This is a little different this time, and there's a lot more complexity to CMIS, but it helps the host ASICs and others get the information that they need, what the status of the module, where it is, how you control it, because there's a lot of handoffs now that go back and forth between host ASICs and optical modules because of the complexity of equalization on both sides. And then, highlighted down here, the variants, and I missed this on the other slide, but the 128 GFC shortwave, that's 100 meters, primary variant in fiber channel, and that would be on OM4 and OM5 fiber. I think OM4 is probably the most prevalent. OM5 actually handles another wavelength, 900 plus nanometer wavelength, a little better, but we're only using single wavelength on this right now. And then a 2 kilometer and a 10 kilometer single mode variant. So this is kind of an eye chart, and I'll go to the next one and kind of highlight it. But I think what this common management interface spec highlights, what it's going to do is give the host ASICs a lot more information about the module, and we'll be able to do a lot more settings, read a lot more of the states of the internal module, so we can make decisions on host ASICs when we should start adaptation and stuff like that. And the timings on fiber channel, and this has always been key, and I know there's been a lot of discussion about link up times and stuff like that. The timings to bring a link up have gotten longer and longer because fiber channel goes through link speed negotiation automatically, which identifies the maximum rate at the other end, and then does training to make sure that we have the link quality we need before mission mode. But I think what's happened because of the complexity of the equalization, both in modules and in the host ASICs, to be able to close these link budgets at really incredible data rates. If you look at how fast these are running now, it takes a lot longer for them to adapt, and it takes a lot more information exchange between the module and the host ASIC to make sure that one or the other doesn't start adapting before they get a good signal. Because what happens then, if you do a misadaptation, you have to do a link reset, which nobody wants to do. So I think this is key, and these type of things are lessons learned from 64 GFC. And I think one of the things that's a little different because of the CMIS support, and when you go forward, we always have backward compatibility, which you'd expect. So a 128 GFC cage, you can plug a 64 32 module in. What's a little different this time is a 128 GFC module, you're not going to be able to plug into a 64 32 cage. Not sure why you would want to, but that is something that has changed a little bit. And fiber channel, because we've always used hardware rate select pins, and for the slower speeds and backward compatibility, we don't want to get away from that, because somebody might plug in a 32 GFC module expecting this. We basically are working with the OIF and CMIS standard to make sure that the requirements that we have and we need to make fiber channel backward compatible and plug and play like it's always been are met. And I just want to highlight this just quick, because of the FEC now, and because of the different links. If you look at this, basically what I'm calling the reclockers are basically the optical modules. We have an electrical link B, an optical link C, and another electrical link D. We have to basically be able to close the budget A to F. And to do that, we have to understand what errors we get on each link and what would be correctable by the RSFEC that the committee has chosen to use. And I think when you do that, a lot of work goes into this, and understanding what can be corrected with the RSFEC random, how long a burst can be impacted, etc. That's important. But I think one of the biggest things that you get out of this is the people that do these analysis, they'll allocate a bit error rate that you should be able to correct per segment, electrical segments and optical segments. They'll cumulatively put them together and say, look, before you start using the FEC to correct the code words, you should be able to, starting with uncorrected just bit error rate cumulative of about 1.3 times 10 to the minus 4, you should be able to have a final FEC corrected bit error rate of much better than 1 times 10 to the minus 15. And this has been a big change for everybody in mindset too. I think one of the things when you look at this now, and I think everybody, no matter what kind of standard they're working on that is commonly using FEC now, a common parameter people will look at is the number of corrected FEC code words, and if there's uncorrected FEC code words which you don't want. So for every Reed-Solomon code word for the 544, 514, you can correct 15 10-bit symbols. If it goes beyond that, it's going to be an uncorrected FEC code word, which starts to give you an idea of what the link quality is. You like not to see them, but in fairness, you would need, they are completely recoverable. And you would need a pretty large number of them to start getting in a position where it's actually affecting your throughput. But so the parameters now are a little different. It really is no longer the simple just bit error rate. It really comes down to then what are the FEC corrected and uncorrectable code words. And I think we kind of, I won't dwell on this a lot. I mean, we've talked about this quite a bit already. For 128 GFC, we're using a block code called Reed-Solomon. It's 544, 514. The bits used in this, a symbol, a Galois field symbol in this is 10 bits. You basically can correct 15 of these 10-bit symbols of 5140 bits sent. If you have more than that, then you will start getting uncorrected FEC code words. So, and we talked about we should be able to work from just a simple bit error rate of 1e to the minus 4 and have extremely low uncorrectable FEC code words. So I think that the same kind of metrics were used in 64 GFC. So, forward error correction really becomes a big part of this. And I hit on this before. The effect basically that we're using goes down to the fire code we used for 16 GFC that wasn't needed for optics. And I highlighted this earlier when somebody had asked, because somebody had asked why we were running at 28.9 for 64 GFC instead of just doubling it to 28.1. And bottom line is we had 160 additional parity bits we needed, and we needed the additional line rate to be able to account for those. So I think this is one of the highlights, and the 128 GFC speed negotiation and 128 GFC transmit training and actually mission mode. In Fibre Channel, I think one of the great things has always been there is a link speed negotiation and we're backward compatible. So it really is plug and play. You have optical modules, you plug them into a cage, you don't know what's on the other end, and the link itself is able to determine what the maximum rate of the partner is and then runs at the maximum speed that's supported by both sides. I think that link speed negotiation is just one of the hallmarks of Fibre Channel and makes it backward compatibility and very plug and play with new systems that could be easily upgradable. Where you could go ahead and get a switch or an HBA that is a higher speed, but not utilize that yet and still work with speeds that are further back. I think one of the things when we went to 64 GFC, because of the complexity of the DSPs and the modules, there were a lot of lessons learned from that. And I think when we did the framing and signaling standard, we left a little bit too much up to choice and didn't make things all completely mandatory, which made some of the link times a little longer than you would want, and also made interoperability a little harder. I think both at 128 GFC, the guys working on the framing and signaling took into account those lessons learned and made sure that everything was clearly spelled out. And the benefit now is we don't have the speed changes that were required in the training frame. And this is a little further in another slide, but I'm just kind of talking through this right now. In the training frame, now you basically have a marker that tells the other end what you're capable of. You have a control, basically control and status frames that are run using Manchester encoding. So even with not the best bit error rate, you're still going to be able to read them on the farther end because they run an eighth of the nominal signaling rate. And you'll communicate back and forth then what the capability is on each end using that, which I think is going to make 128 GFC speed negotiation much, much more seamless than basically 64 was. And the group also was very careful on how you allow transitions. Once you have decided on a speed in LSN and you move to training, the group was very, very careful this time to explicitly spell out what encoding you have to use when you start. And if it's a PAM4 base, you just start at that and there's not switching back and forth. So I think that type of communication is going to help make 128 GFC much more seamless. Now, I think somebody at one point had asked the question, there is from LSN, the link speed negotiation, all the way through training complete, there is a link timer. It's 10 seconds in 64 GFC, and it's 30 seconds in 128 GFC. But I think because of the work the teams did, you'll find that at 128, things will be a lot more seamless. So, and transmit training, the only thing I want to highlight here, we go into the training. Really, the training in this case is in an electrical, if it was an electrical lane, you would be exchanging coefficients for far end transmit settings, whether you want more precursor, less, using kind of the KR algorithm. Transmit training for optical, we're not exchanging optical parameters like I want more power or anything like that. Really what it is a time we picked a data rate, we've decided on what FEC, and now we're giving the equalization in the link time to adapt at that data rate. So you'll make the transition from the speed you ran speed negotiation at to the speed you expect to run the link at, the highest negotiated speed. And then you'll go ahead and give both the optical module and the host ASIC time to adapt. So, I mean, that's kind of the long and short of that. There was discussion at 128 about potentially having some in-band training optically, but we chose not to do that. 4-lane, we chose not to do a 4-lane variant for 128. It would have been a 512 variant, so because it had been 4 lanes at 128. You know, we did a 7P, and the documents are different too. I'll point out when we finished FCPI 7, we released it, and then we got a new standard approved 7P, and we went off and developed that parallel standard. We chose not to do that for 128 GFC, and there is no plans. I mean, we've moved on to FCPI 9, so I would expect there would not be a parallel development at this point. And then 256 GFC, what we're hoping, and this gives a high level, you know, it's improved now from INCITS, the FCPI 9 ad hoc, which they've changed the names to expert groups in INCITS. We've already been working on it for a while. You know, as always, it will be backward compatible to 128 and 64. The goal will be same external connectors as 128 and 64. Existing cable assemblies will work. And as a starting point, our goal, of course, is going to be 100 meters reach on OM4, OM5. You know, we'll have to see if that is actually feasible or not, but that's the goal. And then the single mode cable plant will have a reach of 10 kilometers. And the 256 should double the throughput in megabytes per second of 128 and maintain an extremely low corrected bit error rate target. One of the big things I want to highlight here as the group is starting working on this is technology for the VCSELs that go in optics. There's a lot of work to be done yet, and that's going to play into how fast this development moves forward. And the team's looking at other things like, you know, bi-die optics and things like that. But I think that's common for a standard at this early stage. You're just trying to figure out what you can do, and the teams are trying to predict what technology would be, you know, capable years down the road, and then often that's a hard thing to do. And then basically this, I grabbed this, Craig Carlson gave it to me. These are kind of a fiber channel speed roadmaps. One of the things I want to highlight here that's a little different than the numbers I showed earlier, these are full duplex throughputs. And when I tend to use megabytes per second in the previous slides, I used half duplex. So this, you'll basically see this as kind of a doubling. And, you know, 128, like we said, we we just released the PI standard. It's in public review and will be published, I think, very shortly. Framing and signaling is in letter ballot, T11 letter ballot, so I would call it technically stable. And we've started working on the next speed in the committee. And at that, I'm going to hand it back over to Mark.
Okay, great. Thank you, Dean. That was an amazing presentation. We can certainly see that a lot goes into developing the next speed of fiber channel. It's not just simply a matter of turning the dial up and making it go twice as fast. There's a lot to consider, and your team has done a tremendous amount of work to get us there. So yeah, thanks for explaining all that to us. Well, we can take a little bit of a pause here. If in the audience, if you have a question, we have a number of questions that have been submitted, but if you'd like to submit a question, we still have a few minutes left. Please post those now. Maybe we'll take a break and hear from Kieran. Kieran, was there any questions that we could talk about now?
Yeah, no, thanks, Mark, and thanks, Dean, for the presentation. I literally you answered a lot of questions. I interjected, so thanks for answering those right in the middle of the presentation. One more question is basically low power fiber channel specifications. Are we is there any plans for that, or was it dropped in 64 gig? Basically, can you elaborate a little bit on that?
Yeah, we don't have. We had worked on an energy efficient document or section in one of the protocol documents, but we have not further pursued that. So there at this time there's nothing going on in the standards group that's directly addressing energy efficient.
Right. I think it's becoming important, but right now people are more thinking about reliability and reach, basically on the optics side at least. So yeah, but thanks for the question, and thanks for the answer, Dean. And that's about it. That's all the questions we have for now. Okay. So back to you, Mark.
All right, thanks, Kieran. Yeah, so that concludes the technical part of our presentation. Just a kind of a reminder, we'll be at Flash Memory Summit. The FCIA is going to have a booth there, and we have a theater presentation. So for any of you that are at the Flash Memory Summit, please stop by our booth and say hi. I'll be there. Kieran will probably be there. So come on by. And then, about this webcast, one thing is, now that we're all concluded, we really live off of all the feedback we get from everybody that attends these presentations. We've got the feedback that you like the technical content, you like the basics sometimes too. So please give us feedback on how you like this presentation. All these questions we have, in fact, we have some we didn't mention, but we'll put those all in our Q&A blog, which will be on our website at fiberchannel.org. That'll be accompany this presentation. And then also, follow us on Twitter at FCI News. We'll get more information on the next webcasts. And we have a big library of these webcasts that we've done over the years, and you can find them at our website under the webcasts section. But there's all kinds of great content there. Fiber channel fundamentals, a lot of detail on FC NVMe. We get a lot of questions on that. And then all kinds of topics, from basics to the new speeds to even FICON. So some pretty exciting stuff. So with that, I thank you all. Thank you for attending the webcast.